We all have this image of black holes, right? They're the universe's ultimate prisons. Gravity's so intense that once you're in, you're in. Nothing gets out, not even light. For a long, long time, that was pretty much the end of the story. But what if it wasn't? What if these cosmic monsters, these points of no return, could actually die? Yeah, let's get into it. So, for the longest time, the rule in physics was simple. It was like absolute. Once anything, a star, a planet, you name it, crosses a black hole's event horizon, that's it. It's gone forever. A one-way ticket to oblivion. The black hole only ever gets bigger. It never, ever shrinks. Period. But here's the thing about science, right? It's basically a long history of broken rules. I mean, for centuries, we were absolutely convinced the Earth was the center of the universe. The whole Ptolemaic model, it was elegant, it made sense, and it was completely wrong. New evidence just blew it out of the water. And that's such a great reminder that even our most deeply held fundamental rules can turn out to have some serious cracks. So that brings us right to the heart of what we're talking about today. What if that ultimate rule about black holes was wrong? What if the universe's most perfect, inescapable prison actually has a leak? What if black holes aren't forever? Okay, so to really get why this was such a huge revolution, we first have to understand the old way of thinking. Let's take a look at the classical black hole, the one that comes straight from Einstein's theory of general relativity. Now, the defining feature here is the event horizon. It's a great name for it. The best way to picture it is like a waterfall, but instead of water, it's space itself, just pouring into the black hole faster than the speed of light. And once you cross that edge, there is no swimming back. No way! You are headed straight for the singularity at the center. And in this classical picture, black holes were just simple, weirdly simple. They had zero temperature, and physicists believe they had zero entropy. And entropy is just a fancy word for messiness or disorder. So they were perfectly orderly. They were just cosmic dead ends. Anything that fell in was just gone, wiped from existence. All the information about what it was, its very essence, poof, erased from the universe. Okay, but this super simple, elegant picture, it ran into a huge problem, a massive problem. It basically collided head-on with another giant of physics, and suddenly we had a real paradox brewing. And look, this wasn't some minor disagreement you could just sweep under the rug. This was a full-on, head-on collision between the two absolute pillars of 20th century physics. You've got general relativity on one side, the laws of gravity and the very large, and thermodynamics on the other, the laws of heat and energy. This really lays out the conflict perfectly. On one hand, general relativity says a black hole has zero messiness, zero entropy. But on the other hand, a cornerstone of physics, the second law of thermodynamics, says that the total messiness in the universe can never go down. So think about it. What happens if you throw a hot cup of coffee, which has plenty of messiness and heat, into a black hole? Poof! Its entropy just vanishes. That is a flagrant violation of one of the most fundamental laws we have. So you see, this was a real crisis. It couldn't just be ignored. It meant one of two things had to be true. Either general relativity was missing something, or the laws of thermodynamics, one of the most solid foundations in all of science, were just plain wrong. Something had to give. And this is where a young physicist named Stephen Hawking comes into the picture. He shows up with a truly revolutionary idea, one that would completely change how we see the universe forever. Hawking himself summed it up perfectly. The title of the chapter in his famous book, A Brief History of Time, says it all. Black holes ain't so black. It's just brilliant, and it gets right to the heart of his discovery, that these things are not the perfect pitch-black voids we always imagined. Now, this idea didn't just pop out of nowhere. The scientific community was already kind of circling this problem in the early 70s. You had Soviet scientists like Seldovich and Starobinsky with some early thoughts. Then a graduate student named Jacob Bekenstein made this incredibly bold claim that black holes must have entropy. And get this, Hawking's first reaction was to argue against him. He thought Bekenstein was wrong. But after some key conversations in Moscow, he went back, reran the numbers, and decided to mix quantum mechanics into the equation. And what he found was stunning. It all came out in his groundbreaking 1974 paper. So, how does it actually work? How on earth does the universe's ultimate prison spring a leak? Well, the answer doesn't come from gravity. It comes from the strange, fuzzy, and downright bizarre world of quantum physics.
Okay, hang on, because this is where things get really wild. According to quantum mechanics, what we think of as empty space isn't empty at all. It's a bubbling, frothing sea of what are called virtual particles. Pairs of particles and antiparticles that pop into existence for a fraction of a second, and then poof, they annihilate each other and disappear. But if this happens right on the edge of a black hole's event horizon, something crazy can happen. One particle of the pair might fall in, while its partner escapes. And that escaping particle is now all alone. It has nothing to annihilate with, so it becomes a real particle and flies off into space.
But here's the catch. Energy can't be created from nothing. So the energy to make that particle real has to come from somewhere. And it comes from the black hole itself. So from our perspective, way out here, the black hole isn't perfectly black. It actually glows, very, very faintly. And over unimaginable amounts of time, it's losing mass, particle by particle. It's slowly evaporating. And when I say unimaginable amounts of time, I am not kidding. Just look at this number. That's the estimated time it would take for a black hole the mass of our own sun to completely evaporate. That's a 2 with 67 zeros after it. It's a number so mind-bogglingly huge that the entire age of the universe, from the Big Bang until now, is just a tiny, insignificant blink of an eye in comparison. So Hawking's theory was just this monumental achievement. It beautifully solved that big paradox with thermodynamics, but as great science often does, it opened up a whole new can of worms, creating new puzzles and profound consequences. And it sent astronomers on a very real hunt for proof. And the implications are just fascinating. For one, a black hole gets hotter as it shrinks, which is the complete opposite of how most things work. This leads to a spectacular, violent burst of gamma rays in its final moments. But it also creates this huge new puzzle called the black hole information paradox. Basically, if the radiation coming out is totally random, what happened to all the information about the stuff that fell in? It's a massive deal. And all of this is a huge pointer toward the holy grail of physics, a unified theory of quantum gravity.
So obviously we can't wait around for a sun-sized black hole to evaporate. But the theory predicts that tiny, microscopic black holes may be created in the Big Bang, could be reaching the end of their lives right now. So telescopes like NASA's Fermi are scanning the sky looking for those final telltale flashes of gamma rays. Finding one would be the smoking gun, the ultimate proof that Hawking was right.
And that brings us to the final, really mind-bending question that physicists are still grappling with. If a black hole dies and the radiation it emits is completely random, where does all the information about what it swallowed actually go? Think of all the stars, the planets, everything with its own unique identity that fell in. Is that information just lost forever, wiped from the universe? Because if it is, that breaks another fundamental rule, this time from quantum mechanics. And that right there is one of the biggest, deepest mysteries in all of science today.